Right, so now we can finally move on to our last theorem involving parallelograms. So if let's go back here, you can see that the first theorem was talking about the both pairs of opposite sides being equal and both pairs of opposite angles being equal. The second theorem was talking about the diagonals bisecting each other. Now the last theorem is talking about one pair of opposite sides are both equal and parallel. Using this theorem is such a powerful theorem because if I can just prove that one pair of opposite sides are equal and parallel, I have a parallelogram. So I don't have to do both pairs. I can just do a single pair, right? So that's the power of this theorem. And so let's start proving the theorem so we can use it. If one pair of opposite sides of a quadrilateral are equal and parallel, then the quadrilateral is a parallelogram. And as I've just stated, that you just have to prove one pair to be equal and parallel, and you prove that this quadrilateral is a parallelogram. And so what we will do with theorem 3, remember that when we worked with theorem 1 and theorem 2, if you've been following what I just said intentionally, I've said that when we learned those theorems, we basically proved the theorem, and we used the converse. So what is more useful to us is the converse and not so much of the theorem, because the theorem we treat it as a property. Now with theorem 3, there is no converse. There's no such thing as saying if the quadrilateral is a parallelogram, then one pair of opposite sides are equal and parallel. That does not work. It does not make sense because that's not a property of a parallelogram, right? So this is why theorem 3 is, we only use it as a theorem. There is no converse to it, okay? But I will put a neat diagram towards the latter part of this video so that you'll see exactly what I mean by theorem and converses, right? So what are we required to prove? You'll be given a quadrilateral, right? So we need to prove that ABCD is a parallelogram. So what we need to do is draw quadrilateral ABCD, and we need to make one diagonal, right? Now what we will do to prove this theorem, if you look at the end here, we're trying to prove that the opposite sides are parallel. Now if you go back to this list of all of the theorems here, right? Yeah, if you go back here, can you see what is the first idea that we talked about? What is the first theorem that we talked about? Both pairs of opposite sides are parallel, right? That's the first theorem of a parallelogram. And so what we'll do is to prove this last theorem, we'll make use of the first theorem, right? So if I come back here, that's what we're trying to aim to get to, right? So when we're drawing these triangles, it'll be A, B, and C, right? And it will be ADC, right? And the reason we'll do that is because I need to find something about these sides. Because if I can prove that this is parallel to that, and this is parallel to that, only using, listen to what I said, only using one pair of opposite sides equal and parallel, then we have a parallelogram. Let me reiterate that. I'm starting off with a quadrilateral, and I'm given that there's one pair of opposite sides equal and parallel. If I can prove that the other pair is parallel, then by extension I have two pairs of opposite sides that are parallel. Therefore, I have a parallelogram using the first theorem. Understood? So this is not a parallelogram. This is a quadrilateral. But if I can prove that this quadrilateral will lead to a parallelogram, and how am I going to do that? Is by proving, right? So what's the how? How am I going to do that? Is by proving both pairs of opposite sides parallel, then this quadrilateral becomes a what? Parallelogram. But we're starting off with what this theorem is telling us, what the theorem tells us. All the theorem is saying is, if you're given a quad and you're given one pair of opposite sides equal and parallel, automatically it's a parallelogram. But now I'm telling you why. So this theorem is telling us why is that the case. So let's do this. Start off with triangle ABC and triangle ADC. And the reason I chose these two triangles strategically is because I want to find out, I need to draw conclusions about these sides. Right. So in triangle ABC and triangle CDA, the first statement that we can make is angle A1 is equal to angle C2. So this angle here is equal to this angle here by reason of alternate angles, and we'll say that AD is parallel to CD. Then we can see that AC is common. So this side here is common between the both, so therefore they'll have the same length. And lastly, we're given that AD is equal to BC. So that was from the theorem. It is given that the opposite sides are equal, or we could say that AD is equal to BC. So what we effectively have here now is a side, an included angle, and a side. And so if we look at this, from the 5 conditions that we learned in congruency, we have side, 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 angle, side, angle, side, angle, 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 side, right angle, hypotenuse, side. And so from these 5 conditions, we made use of the second one. So now we have already proved that. So now what's our next step now under congruency is naming these triangles. So let's look at triangle 1 and triangle 2. Let's match the angles so that we can name these triangles in the correct order. In triangle 1, angle C is equal to angle A in triangle 2. In triangle 1, angle B will be equal to angle D. Right? And why? Why am I saying this? How do I know this? Look at the side that is common. See this triangle here, the side here AC. This side here is common to both triangles. So what angle is opposite that side? B. What angle is opposite to that side? D. Understood. Look at this triangle BC. BC is equal to AD. What angle is opposite BC? Angle A. What angle is opposite AD? Angle C. So we can say that in triangle 1, C is equal to A. In triangle 1, B is equal to D. And in triangle 1, A is equal to C. And so according to how I labeled it here, ABC, according to how I labeled it here, it'll go CDA. I can take these letters in any order. I can say BAC, but then I'll have to change the order of these letters. It'll be DCA, right? But obviously I chose ABC, so this will be CDA. And so therefore we have triangle ABC is congruent to triangle CDA by reason of side angle side. But what this conclusion enables me to do is extremely important. If I look at this here, in triangle 1, what can we say that angle A is equal to? Angle A in triangle 1 is equal to this angle here, C. And what it does now is, it does something very, very important. The fact that these angles are equal implies that these sides are parallel. And so exactly what I've been telling you so far, that we have theorems and we have converses. Right. So what I taught you and what your teacher would have taught you was theorems. So basically, if I look at this scenario, I can say that alternate angles, right? And I'll just state the parallel lines. Remember, AB parallel to CD. But now we are not making use of the theorem. We are making use of the converse. So if, listen to this, if we have parallel lines, then the alternate angles are equal. We can go in the reverse direction. If the alternate angles are equal, then we have parallel lines. And so what's important and what's significant is your reasoning changes. Your reasoning changes because you're not using the theorem, you're using the converse. And so what we can say is that because these angles are because the alternate angles are equal, then the sides are parallel. And what's your reason? Is that alternate angles are equal, and in brackets you must put converse. And so that's why you're telling your teacher that you understand what you're doing. You're telling them I'm not making use of the theorem. Because if I made use of the theorem, then I'll say that A2 is equal to A1 by reason of alternate angles AB parallel to DC. But obviously we cannot do that because we are not given that these sides are parallel. We are proving it to be parallel. And why we're proving it to be parallel is so that we can conclude that ABCD is a parallelogram since the opposite sides are parallel. And again, as I said, we made use of the first theorem. Now, you have to understand this. Understanding the difference between theorems and converses, you have to understand. Right, so can you see exactly what I am saying? See, look at the two different ways that we stated alternate angles. Here, we use the theorem. Here, we're using the converse. So I want you to go back to lines, angles, and triangles. And where we discussed the fun angles, the idea that I talked about there was I said whenever you're using the theorem, state the parallel lines in which these angles are formed. Remember I said that. So that's the first thing that you would have written. Now the second thing that I want you to write is everything that we learned there is what we call theorems. So now you need to write the converses. So let's go back there quickly and let me show you exactly what I mean. Right, so if we come back here to our fun angles, everything that we've learned here are what we call theorems. So this is a theorem, this is a theorem, this is a theorem, right? And what we're going to see whenever using the theorem, right, state the parallel lines. State the parallel lines in which these angles lie. Right, very important stuff. Very, very important stuff. You will lose marks if you do not state these parallel lines. And so if we go back to our reasoning, let's go to our reasoning sheet. Right, if you come to our reasoning sheet, there you can see precisely what I was saying. These here, can you see here? Whenever you're using the theorem, you state the parallel line. So that's what I mean by theorem. But whenever you're using the converses, you have to, the reasoning changes. So you'll say alternate angles equal, corresponding angles equal, co-interior angles supplementary. Understood? So these are the theorems and these are the converses. Understood? So when you're using the converse, you need to state, what does a converse state? That alternate angles are equal, corresponding angles are equal, co-interior angles are supplementary. What does the theorem state? That if you are given parallel lines, there's it here, if you are given parallel lines, and that's why you have to state the parallel lines in which the angles lie. Okay, if you want to make all of your notes nice and concise, you can come here and write all of the reasonings. So you'll write here corresponding angles, and state the parallel lines. You'll write here co-interior angles and write here the parallel lines. Here you'll write alternate angles and you'll write the parallel lines. But here when you're using the converses, for the converse, this will become corresponding angles equal. When you're using the converse here, this will be co-interior angles, SUPP, supplementary. And here this will be alternate angles equal. So please note the distinction. So these are the reasoning you will use when you're utilizing the theorem, and these are the reasonings that you will use when you're utilizing the converses. So I hope I stressed that enough. Right, so now if we go back to our theorem 3, right, so these are the notes that you need to add. When I go back to theorem 3, that's basically everything that you need to know. Yes, and so that's everything that you need to know, right? Understanding the difference between the converse and the theorem, and this example basically emphasized what you need to know. Understand when you're using the different theorems and how your reasoning changes and how we swap the if and then statements. And like I said here, see theorem 3, this theorem, for parallelograms, there is no converse. And so that's the reason why whenever you're learning the theorem, ask yourself, is there a converse? Because if there is, then it enables you to do much more broader stuff. But with this, there is no converse. Like, it does not make sense to say that one pair of opposite sides of a parallelogram is equal and parallel. It does not make sense to say that because we know both pairs are. That's the property of it. And so the fact that we can't do that implies that there is no converse to it, right? The converse needs to be examined. It's not always true. It's exactly as I said when we did exponents. I said you can sometimes, not always, go in the reverse direction. So you can go in the forward direction, but not always in the reverse direction. So that's the theorem and this is the converse. Right, so let me put a nice neat summary for all of this, understanding the theorems and the converses, and then you can see exactly what I'm saying, and then we will solve examples dedicated for each theorem. So I'll isolate each one, so you will see how we can put all of these ideas to practice.